Hello dear viewers, today I want to introduce something, a new set of free design spreadsheet from the Reinforced Concrete Center. So we're going to design column uh, from these pre-design spreadsheets. And to design column, the first thing that you should know is that you cannot do any design without doing load takedown. So in design, you start from bottom up, but you need to do the load takedown first. So you need to do the load takedown of that particular column so that you can design. So I will introduce you to a set of design spreadsheets. You can see all these design spreadsheets. I will insert a link in my description where you can download these three design spreadsheets, and you can see how we are going to deal with RCC 51, that is Concrete Center 51, column load takedown design, and RCC 52, column chart generation, and RCC degree, that is column design. And also, if you are designing a circular column, you're going to need RCC 54 column design. So this design spreadsheet that are there in my description are just the way you see them here. Just I have compressed them in that RAR, so you can download all these. They are both in BS and Eurocode. So this TCC Eurocodes and these RCC are BS code. So you can download them in the link in my description. So let's begin. So we'll start with the load takedown, and you need to open these spreadsheets. So the reason why I've put them in a new folder is that you need to be very careful when you are handling these spreadsheets because they can get corrupted. So every time you're designing, you need to know that you have to copy the spreadsheet you're going to need in particular in another folder, maybe in your desktop, so that you're going to be able to design, and you have to have other spreadsheets safe stored somewhere that are not. Maybe you're going to corrupt the spreadsheet, so you have to be careful. So that's why I copied them in a new folder here. And it has to do with to design this particular column for this building here. And you can see this engineer. It has two. You can see I have two types of column only. That means I have one column for the entire structure, and this the other column is for the staircase. So I have only two types of column. So it means when I'm designing, I'm going to just search for the most critical column, and I'm going to design it here. So that is going to be my column for the entire structure. So I'm going to do load takedown where I think it is most critical. So for me, I think the most critical column is this one, because you can see, unlike this column here, it is taking load from this panel here, right? This panel here, and this panel here, and this panel here, and on top of that, it is taking load from this beam here, from here to here, and this beam from here to here, and this beam from there to there, right? And this beam is taking load from this secondary beam. This is the primary beam. It is taking load from two secondary beams, and also this beam is taking load from two secondary beams, this one and this one. So we will need to design this one as our prime or our critical column. That's why you can see, and this drawing has already been approved, and this house has already been finished. So you can see only two types of columns. So we're going to do the most critical here, and you can go and do for yourself. You're going to need to do for the staircase and others. So you will download the spreadsheet. So let's begin. So we'll start with the load takedown. So let me column load takedown, right? So column load takedown looks like this. There's several sheets. So you can see it as like 5 sheets. So the most important is the first, the second, and the last. But the rest are for calculation. So you need to know which values we insert in this sheet. Let me increase it to about 100%. So you need to know what you need to insert here. So you can see clearly this AB, BC, clearly this is AB and this is BC. So those are the spans. So that is you can see from this column, it is column to column, right? So that is the span. So maybe I need to close. Okay, you can just open it. So this is column to column. So AB, let's find the distance AB. The distance AB is the distance from here to here, which is about, I'm not sure doing this up to scale. It's from center to center. So this one is actual. So it is not scaled, right? So the distance between here, you can just use this distance here. Or you can just scale, it depends. You can just use this one. Okay, this one is scaled. So let's the distance between this being is 200, right? So let's make it 200. So that is 200. So we can measure the distance between here and here. So that will give us about 5.5 meters. That is 5,500 millimeters. So you need to know that the span has to be divided by 2 because there is a column on this side and there is a column on this side. But in case there was no column on the other side, you could just use the entire span, right? If there was no column here, maybe it was here, so you could just use. But now because there are 2 columns, you divide the spans by 2. Now this one will be 2.75. So I will go and insert my value here. Let's first enable the content. I insert 2.75. That is our AB. And we have how many floors? I think we have 5 floors because if you see from this drawing here, it is 1, 2, 3, 4, 5. This is the roof floor, but it's like the 5th floor because we have a slab, so we're just going to include it. So BC is just the same distance. BC is from here, that center to that center. That's the same distance. Wait. So we are doing this column, right? So I think let's just measure the distance. We are doing these are not critical for this one. So yeah, I think it is just 5.5 because I think this one will really because this column, this is not really in the center of this line. If maybe we can find the center, because the grids are normally not in the center of the column, but rather on the center of a line, as I've explained in previous videos. So I think this one we can just perhaps move it, perhaps move this. So I want to move the dimension point. So I want to move it to the center of this. So I think you can see the center is not, so that is the center, right? So you can see this 5.5, 5.5. So the grids are usually at the center of one, not column, right? So you can see this column is over the center. So that means it is 5.5, the span will be half of it because the columns are sharing. So it will be 2.75 also on the other side. 2.75. Again, we're going to see the span from this here, from this center to this center is 300 plus 100 plus 1 because the center of this beam is 200 and half of it is 1.6. So 1 2 is 1.6. Again, again this one is 0.2, 0.2 again plus 0.2, that is a 0.4. Divided by 2, it should be about 1.7, right? So we have slabs, 5 slabs, that is first floor, second floor, third floor, fifth floor, and the roof, that is the fifth floor. This is the fourth floor. So our beam is obviously 200 by 450. So we're going to use a beam of 200. So there is okay, we don't need to change anything. Here we need to, let's start by 200, so that we see, and we know the floors is maybe not really distance of 3 meters. It is 2.85. So we're going to change that. This one is 2.85. Right. So our slab is going to be the slab of the circuit of our slab plus the circuit of our slab plus the dead load, that's GK, plus the finishes and the partition wall. So let's say we know that how to calculate the circuit of our slab will be. Unit weight of concrete is 25 kilonewtons per meter per cubic meter, and we know that the depth of our slab is 0.15 or 150 millimeters. So the unit weight will be 0.15 multiplied by 25. That will be about 20. That will be about 3.75. That is kilonewton. Per meter square. That is the concentrated, the distributed load on the area. So that's what we're going to use here. So plus 1, that is about 1.1 finishes and partition wall will be about 4.2. We use, because it is a residential house, we're going to use a live load of about 2. Now, already we can see the load has been distributed. Now we have not done the beam. So the set weight of the beams, that will be the total load on the beam that is being transferred into that column. That will be including the set weight, the weight from the slab, and the weight from wall, that is partition wall, and also the weight from secondary beam. So it is going to be a total of all that. So let's start with this. Let's start with this particular beam here, which has 2 secondary beams. So we know that this beam has a length of 5.5 meters, center to center, and it has a depth of 0.45 and a width of 0.2 meters, right? So we already know the dimension of this. So we know that the unit weight of concrete is 25 kilonewtons per meter cubic. So we know that the dead load or the point load, so the point load stroke the is it concentrated load of that beam will be equals to this unit weight of concrete 25 multiplied by its volume. That will be the concentration. Now that will be equals to this multiplied by that is 0.45, and 0.45 multiplied by 0.2 multiplied by 5.5. But if we want to find the concentrated, the distributed load, that is the uniform distributed load. So the distributed load disregards the length. So that will be just 25 multiplied by 0.45 multiplied by 0.2. That will be about 2.15. 0.5 kilonewtons per meter. Now this one will be in kilonewtons. The above 13.9. So our beam, the dead load of our beam is that. Again, we have to include the dead load from this slab and this slab, and also we know we have a partition wall. Our partition wall is, let's say, because the wall, the clear span is the span of each story to story is 2.85 minus the depth of the beam 0.45. That will be equals to 2.1. So we know that the wall has a height of 2.4. That is 2.4. Don't forget about my handwriting. And multiplied by the width of the wall, that is 0.2. Multiplied by the unit weight of mass on the block, that is 20. You will get about let's say 9.6, right? That is kilonewtons per meter. And then we found that our beam is 2.15 kilonewtons per meter. And then we have load from the slabs. Now this wall, we need to find the load from the slab. To find the load on the slab, you can use this spreadsheet. It's also included, so you can just download them, all of them together. So the load from this slab here is 3.4 into 3.4 into 3.2. That is the Ly is 3.4, Lx is 3.2. So using this spreadsheet, you can find the load, the triangle and trapezoid area. So 3.4 and then 3.2. To find that is 9.87. So we're going to write it somewhere. 9.87. Again plus the load on the other side will be 3 and then 3, right? So just the 3, again 3, so it will be 8.75, 8.75. Those are just those two slabs. We have another two slabs on the opposite side. Let's see. This slab one way, 3 and 1 and 2.1. Let's see. So this one will be 3 and 2.1. That is Lx. Yeah, it is a two-way slab. That is another extra load of. So I'm going to grab this one. That is that is the 7.6 and 9. You can see it is in kilonewtons per meter. Again, we have another slab. We have another slab. We have another slab here. Now this one is 1.7. Let's see if this one is 1. So this one is 0. So 1.7. So it is 6.64. And of course we have these other two beams. So first, if you add these, the total of these, we find, if you add the total, we find that if you add these ones, we find that the total sum is about, let's use our calculator, about 6.64 plus 7.64 plus 9.6 plus 2.15 plus 9.87 plus 8.75 plus 9.87 plus 8.75. We're getting 44, right? 0.65. That is without the load from these secondary beams. So our secondary beams will still have load load. Let's say they still have partition load. So we still have a distributed load of summation of this. That is 9.6 plus 2.1, right? That is 6.5, right? So 9.6 plus 2.15. They still have a distributed load of 11.75 because it is self-weight plus the partition load. So let's say we have that load, maybe let's reduce that because maybe there's an opening, right? So let's reduce to about maybe 9 plus 2, that is 11. And then this load is divided among these two beams, primary beams. So that will be 11 divided by 2, that will be 5.5. So 5.5 by 5.5 till 11. So this load on top of this are 11. So it will be 55.65. That is on which slab, on which beam? That is this one and this one. So they are similar. So we are going to put 5.65 in our spreadsheets. So let me grab everything. I'm going to AB delete that. AB 5.65 change automatically. 5.65. Then here this is just 5.65. Now we also have this the right load is 0. So in the other direction we can still do the same. Now the direction will be load from this small panel. So we 2, 3 and 3. And then we got 8.75, right? So let's just do 3 and 3. And then the 8. That is, so now this the other beam will be its self-weight plus its partition load. Now it is now this beam plus this beam plus the load from let's say this slab only. So now I have secondary beam. So we can just use this the long one. So it will be 3.2 and then 3.4. So we design for the mode before 3.4. Then again 3.2. So let's see. So it's 9.87. Again, that is the slab load. It has a load of 9.6, that is the partition wall. Then that is self width 2.1 steel 5. Okay. And then it has just those. Then other we're using I don't think so. So that would be a total of, if you add to the summation, it will be 7 plus 9.6 plus 2.15. That will be 21.62. Remember, we usually design for the most. So I will pick this just to the entire, even the other side. So 21.62. Again, 21.62. Okay. Now you can say we have another load from, let's say it's the roof of about, so let's assume, I think just the roof load is just a very small load, maybe 5, maybe something like that. So just leave it, not necessary. So we have done the load takedown. Now from here you can already say that we can do what we call preliminary sizing. Now that we know that this column is not sufficient, 200 by 200 is a very small, so it's not good. Center is too small. So now in here we want to do preliminary sizing. So you can increase this maybe to 300. Still not good. Increase it to 400. Still not good. So increase it to 450. Then we have 250. That one is okay. 450 by 250. So you can see if we reduce this one to 200, center is not too good, so we need to increase this to about 25, right? So now the current center is good. Now we have done the preliminary sizing. We need to be economical, okay? If maybe we increase this one to maybe 1,000, because it's not good, center too small, but so you see, you need to maybe, let's say 350. You can use 350 by 225. Good, but use minimum of, what about the by 200 by 500? Center is too small, so just 350, maybe 350 by 225. So maybe by 400. So now this one is okay. So let's see. Okay. So you need to check to make sure that A is okay. A is okay. So can it says 2016. So let's increase this one to 20. It's 20. So let's see. Let's go back to the row takedown. I'm not sure about this secondary beams, but there maybe these secondary beams don't really have let's say they don't have a partition wall. Okay, let's say they don't have partition wall. So because I cannot see the slab layout of this building, so we don't have a partition wall there. We don't have but we don't have a partition because you can see um yeah, we have a partition both of these two. We can clearly have a partition wall there. So let's see that the distribution from here. So we got the center of this beam to be 2.1 plus 9.6. Again, plus the weight from this slab, that is plus, so it's becoming all that. Let's run. So we have done the premier sizing, and but we have not designed it yet, right? So we have not designed this column. So don't worry, because we have another spreadsheet where we can check and do the design. So based on these loads, I just come to the second spreadsheet, that is column design, and we put our loads from here, our load takedown, and we can get what is required. So, but first, we need to be through with this column totally. So we need to design maybe its footing first. So go to third foundation and then put our loads. So you can, when you come to load takedown, you come to the second sheet, you find that the total axle load is 1598 and the moments are 98 and moment is 32. That is in the YY. Alright, so just put it here. That is 1598 and 32.1. No, that cannot be the dead load because we have to be very careful. You see, from our load takedown, we're not going to use 15, we're going to use this is what for our dead load. That is 1110. Alright, so 1110 and level of 11. Moment 36. Then we need to delete this. Then here is 2.5. Here is 500. Now go beyond 500. Let's say 25. So you can see the size, you can see the suggested size here is we can use 2650 square. So let's use 26 suggested size 650. 2650. This is a valid design. Now you can create this. So new foundation into create now. So you can go to column, design, we put our, now we put our, we'll pick that, use our n. So the 25, 68, and 68. Color, take the form. So you can see, let's continue. 968. 648. 3, 25. So you can see the design that we are getting if we use hand by hand, because we still want to minimize this column. So we are getting such design. If we increase this one to 25, we're still getting the same thing. So let's just maybe try to minimize it as much as we can. Because now that the other one is familiar sizing, so we know where it should be around. We have to increase this one now to 3 for the design to pass. Get maybe what we need, right? So you increase this one to 25. Let's see. So you can see our last column was failing. Our last one was failing. So we have to use 225. 1 by 225. So we start by 80, 20, 8, 16, and then we don't use 12 in one column. So I'd rather use, let's say, I'd rather change this one than maybe use 12. I'm going to change them to 16. So let's see the design, the column as it was designed. So the only place that maybe got 2000 is foundation footing. Also we got 15 D16 at 140 and 5016 at 140. For the column we got 8, T8, you can see T20. So this one is T20, 8 of them. So this one is 6 plus 2. Alright. Again, we got the same thing. Maybe if this engineer used, let's say, Procon. Let me open Procon. Because you can also use Procon if you have done analysis, your analysis are located down correctly, and see give you those results. So if you do not use a spreadsheet, use Procon. So let's compare our spreadsheets with Procon. Okay. And again, you can see is sizing is 200 by 400. So we are about there. Our design is very safe, and of course, maybe the place where we differ is maybe how it is low takedown. That's how we go about it. So let's compare the results with Procon. So maybe I can go to concrete, and then I can go maybe to base. Let's first design the base. That is the part footing. And so we are having, let's fill in the data. So our baseline, this input has to be changed. So row default. Our file, I'll go to units, and I'm using metric. I don't know why it's giving me input, but we can do the file input metric. Okay. So I'm now using metric. So and then design code, I'm using BS, right? So let me save the data. Right, I'll load some of my defaults. I'm going now to, I see we need to fill data FY is of course for 60, FCU 25, base 20, FCU we can just use less than this, maybe you can use 20. Then overturning one, the maximum serviceability, that is the load has been carried down, maximum is maybe 1,000. So from our load takedown, you can see it's more, even more than 1,000, right? That is unfactored load. So from our load takedown, link this one is unfactored cumulative load, right? Now this one is total. Okay, so this is the dead load, then live load. So and we have these moments, they are very minimum, but I'm just including. So let's put ABDs. See, that maybe 2,000, maybe 2,000. Then our column is, let's say, so 0.45 by 0.225. Right. So we can use this. So this one is 2 by 2 because it's 9 meters. Then 2 meters is being 200 and something. So the kilometer is 1598. Answer. P is 1598. In case one column is wrong. So I'm going to design. Okay. You can see we are getting almost the same results. Okay. T20s, but for columns, I didn't think we use N. Let's definitely use GK very well. So we put that value. But anyway, we will focus on that on another because we already calculate for our column. So point 3. So if you do the design, okay, you can see they should not be red lines, so this indicate failure. So should just come here, maybe increase this one to 2.4, 2.4. The tab height, the depth, and then the cover soil should be increased, and then you can also increase the depth of the beam to 5, the base to 0.5. Then you can put these factors as they are here, 0.9, and then 1.2, then design. So you can see now uh, the the base is passing here in Procon, and get the calculation and everything. So you suggested, okay. So you can see 16 at that. So the column, we have already designed the column, so you can use the calculation from Procon. So you're getting here 90, 16 at 300, and the base size is 2.4, 2.4. So uh, maybe that's why you're getting some difference, maybe. But the column for sure, you're getting the same thing, 8 to 20, to now the T16, and like that. But that's how you do the takedown. So probably the difference would come on the way he calculated manually here, or whether you how he included the weight of these uh, um, um, secondary beam, or whether or not the walls were bearing or not. So and such stuff and such stuff. So it depends on a lot of circumstances. Okay, so that, thank you. Please don't forget to subscribe to my YouTube channel. And of course, I will upload more videos like this. So subscribe so that you will not miss out. And you can download also my spreadsheets. And I hope you will like this video so that YouTube can be able to rank my video so to know that it's a good video. Thank you.